The idea of set is one with which we are all acquainted in ordinary life. We all recognize the properties common to a specific group of objects. The individual members that make up this set of pieces of chalk or this set of pencils all have something in common. The first set, that all the members are chalk. The second, that all the members of it are pencils. Examples can be found everywhere. In the classroom, a teacher could use a set of chalk or pencils or books or the desks the children sit at to get this concept across to his pupils. The important thing is that we are able to tell of each object whether or not it belongs to the set we're talking about. This same concept occurs in all branches of mathematics. There are sets of numbers and sets of points, as well as sets of books and pencils. For example, there is the set of even two-digit numbers, or the set of all odd two-digit numbers, or, if we wanted to, we could limit a set at will, defining it, for instance, merely as the three numbers 1, 2, and 3. Until now, this notion of set has not largely entered the high school classroom, and it's time that it did, because it offers three important advantages in our teaching. It brings clarification, putting our ideas into sharper focus. It offers simplification. The very language of sets helps us to eliminate vague terms and trim off excess verbiage. Finally, it gives unification, since the concept of set pervades all areas of mathematics. Although formal set theory certainly should not be part of a high school course, the concepts and vocabulary of sets, presented quite informally in the classroom, can arouse interest in students and promote fuller understanding. For example, let's visit a class whose teacher is introducing the idea of variable from this point of view.
We've spent some time discussing what a set is, and I'm sure you all understand what we mean by it. Let's take an example. Our set, which we'll designate by the letter S, is all of the states in the United States. I'm going to make some statements about its members or elements, and I would like you to tell me if these statements are true or not. The state of Virginia is one of the original 13. Is that true, Joan?
Why, yes.
If I take out the word Virginia and replace it with a blank, is that true?
It isn't true or anything now.
In other words, it's neither true nor false until I replace that blank with one of the elements of the set we're talking about. This is what we call an open sentence because, well, it's wide open, isn't it? If I put the word New York in there, is that true, Barbara?
It's true.
To reinforce the concept of an open sentence, our teacher uses various replacements for the blank space, some true, some false. Then he can introduce the idea of using a letter as a placeholder.
There. I have a sentence, and it has one variable that we're calling Z. Regardless of whether the sentence is true or false, what can we replace Z by?
The name of any one of the United States.
That's good. Any one of the elements of our set can be the replacement, can't it?
Yes, but it will be true only 13 times.
That's true, but the variable here, z, would still be a placeholder for one name selected from the collection of possible replacements, one element of our set, which in this case is all of the states in the Union. Yes, Richard?
I understand this, but what does it have to do with mathematics?
In mathematics, instead of sets of states, the sets are often made up of numbers.
All numbers?
No, only those numbers of the set that we have decided to use as replacements. We call this the universal set, and we use a capital U to designate it. If my universe or replacement set is the numbers 1, 2, 3, 4, 5, 6, and 7, it represents everything, every member that we can use. Could I talk about an 8?
No, it's outside the universe.
Janice has the idea, all right. Now here's an open sentence for you with one variable. X plus 3 equals 7. Suppose we try all the possible replacements for our variable x. 1 plus 3 equals 7.
But that's not true, Mr. Mewiney.
Correct, and so we'll do this. Let's keep all the false statements in one column, shall we?
Mr. Mewiney has his class substitute values from the universal set.
4 plus 3 equals 7.
Now that's true, Mr. Mewiney.
A new column is made up for the one true statement, 4 plus 3 equals 7, and then the class continues until it has substituted all possible values from the universal set.
Well, have we run out of possibilities for our variable?
Sure.
Yes.
Martha, what numbers from our set did we use that gave us false answers?
1, 2, 3, 5, 6, and 7.
Now, that's a set of numbers. They all have something in common. What is it?
They all gave a false answer.
Right. And all the members of this set were also members of U. And so let's call it a subset of U. I'm saving subset 1 for the true answers. Now, Barbara, is there a set of numbers that gave us true answers?
Only one. The number 4. Can that be a set all by itself?
Indeed it can. And so we have another subset of U that consists of the one number 4. Now we have two subsets of the universal set, U. On what basis did we divide the universal set into two subsets? Why did we put some numbers here under false and one number here under true?
Well, it's all whether or not x plus 3 equals 7.
That's right, Janice. This statement here really selected the two subsets, didn't it?
Yes.
And that's why we call it the set selector. Now, class, which of these two subsets gives us the solution to our equation?
S1.
The true set.
Good. So we'll just call S1 the solution set, because it's the set of replacements that makes the sentence true.
Now let's explore some of these ideas we've seen discussed. First, we'll talk about solution sets. The replacement or universal sets used in high school algebra are usually all or part of these number systems: integers, rational numbers, real numbers, and complex numbers. It's most important that we keep in mind which of these systems is the universal set for the particular problem that we have under consideration. It makes a great difference. For example, consider the expression x squared minus 2. If we are working in the field of rational numbers, we would say that this expression cannot be factored. It has no factors with rational coefficients. However, if we are working in the field of real numbers, we could write these factors. Let's look at another example. This time, we shall take an inequality as our sentence in one variable. The possible replacements for the variable x will be determined by the universal set or the replacement set that we specify. If u is the set of rational numbers, the replacements will include all possible whole numbers and fractions. But if u is the set of all positive integers, the possible replacements are limited to these integers. Here, the sentence in one variable, x is greater than or equal to 5, is the set selector. The set of positive integers for which the sentence is true is 5, 6, 7, 8, and so on indefinitely. This is the solution set. We can picture this graphically. On the number line, we'll indicate the elements of the replacement or universal set by small circles. The solution set is indicated by the dotted circles. A convenient notation is this. The vertical line stands for such that, and the whole statement is read, the set of all positive integers such that x is greater than or equal to 5 is the set consisting of 5, 6, 7, 8, and so on. The left side of the equation is called the set builder. One of the changes in content being suggested for high school algebra by those interested in curricular reform is the inclusion of work on inequalities. The notion of solution set is particularly helpful in teaching this work because the solutions of inequalities are often, as in our last illustration, sets of many members, whereas equations at the 9th grade level generally offer solution sets consisting of only one or two numbers. Another reason for the inclusion of inequalities is that they offer a large variety of possible open sentences. For example, we can discuss the sentence, x is greater than 5. We can make a new sentence by merely adding an equal sign. We can change to x is not greater than 5, or we can change to x is not greater than or equal to 5. This offers a variety of problems arising from the same situation in which the notion of the solution set can be developed. Even in dealing with equations, however, one can express the facts commonly taught about solutions very simply in set language. For example, a quadratic equation has precisely two real or imaginary roots which may be equal. This fact, commonly taught in 11th grade algebra, may be expressed by saying that the solution set has two members. As indicated earlier, the language of sets offers simplification as well as clarification. So much for these notions. The language of sets offers unification of an equation and that of an inequality. The notion of variable itself is a good example of how the language of sets clarifies ideas that might otherwise be fuzzy. In Mr. Mawhinney's class, students learned that a variable is a placeholder, a symbol in a sentence that holds a place for or may be replaced by the elements of a given set. This is sharp and precise. But try saying it without using the word set. Either the statement is incomplete or it is vague and inaccurate. We have to use descriptions that are far from precise, such as a general number, a literal number, or a changing number. These same ideas are applicable to sentences that do not contain numerical variables. For example, consider this sentence. At various times, from 1787 to the present, the replacement set was differently constituted, and at different times, different states were the largest. From 1845 until 1958, the solution was Texas. In 1958, Congress changed the replacement set. Thereafter, the solution became Alaska. And at different times between 1787 and 1845, this sentence had different solutions. The solution depended on what the replacement set was at the time. That is, what states were in the Union at the time the solution was sought. Now let's go back to the idea of set builder. This, as pointed out, is merely a notation, but it is a particularly fruitful notation. It enables us easily to talk about all the x's, or rather, the set of all x's that satisfy some specified condition. And determining all the x's that satisfy some condition is precisely what we do when we solve an algebraic problem. Here are a few examples. The set of all x's such that x squared minus 5x plus 6 equals 0 is the set consisting of the numbers 3 and 2. The set of all x's such that 3x squared minus 20x minus 7 equals 0 is the set 7 minus 1/3. For 3x squared minus 20x minus 7 equals 3x plus 1 times x minus 7. The set of all x's such that x squared is less than 4 is all the numbers between minus 2 and plus 2, not inclusive. The set of all x's such that x is divisible by 3 and also less than 20 is the set consisting of the 6 numbers 3, 6, 9, 12, 15, 18. All of them are suitable for classroom use. Once the novelty of the language and the notation has worn off, it will indeed be found that these techniques do offer clarification, simplification, unification.